Okay, let's start with our second part of the class today. Yeah, we completed our third lecture by learning how to calculate entropy and information gain and how to construct a decision tree from that. Okay, those are the steps followed by ID3 algorithm in order to construct a decision tree, optimal decision tree. At each step, finding out which attribute will serve as the best classifier to classify the training examples that haven't been classified so far. Okay. Now, in this class, let us see what is hypothesis-based search in decision tree learning and inductive bias in DT learning. Okay, now what does the hypothesis space searched by ID3 contain? In finders algorithm, we know that the hypothesis space contains all the hypotheses or statements that suits the training examples, that covers the training examples. Even in candidate elimination algorithm, we have a version space which will cover the most generalized hypothesis and most specialized hypothesis, right? So those candidate elimination and finders algorithms use the hypothesis space in order to search for the best fit hypothesis according to the training examples given, consistent with the training examples given, right? Now, what is the hypothesis space searched by this ID3 algorithm or by the decision tree algorithms? What does it contain? ID3 performs a simple to complex hill climbing search through this hypothesis space, right? So in this hypothesis space, it will perform a simple to complex hill climbing search. Means, say, actually hill climbing is in the reverse direction. It starts with a root node, then it proceeds further, checks for a best fit attribute, proceeds further until it reaches better classification, right? That is the search, that hill climbing search that is followed by this decision tree algorithm. Why we call it as hill climbing is, see, if a person starts at the foot of the hill, in order to climb the hill, he'll take the highest inclination around him which is possible. In this case, in decision tree, he'll take the highest information gain. Both are analogous to each other. I can compare both of these, right? Say you're standing at the foot of a mountain. In order to climb the mountain or hill, what you do? You just search around you. And wherever the inclination is steep, means wherever you have the highest inclination, there you tend to go forward, right? In the same way, decision tree proceeds with the hill climbing approach. Means whenever it stands at a root node, how it proceeds further, it tries to calculate the information gain with all the attributes and finds out which attribute is giving the best information gain and proceeds with that attribute further. Okay, that is why we are calling it as hill climbing search. Okay, and it proceeds from simple to complex. Say your decision tree is only this much, it is a simple decision tree, but if it goes on to various levels, then it starts becoming complex, right? So this ID3 performs a simple to complex hill climbing search through this hypothesis space. So the hypothesis space in decision tree learning is nothing but number of decision trees. And what is the best hypothesis? What is the best fit? The optimal decision tree. How is this optimal decision tree found? By implementing the measure of information gain. Okay. Now, beginning with the empty tree, it considers progressively. Progressively means as it proceeds forward. Beginning with the empty tree, it considers progressively more elaborate hypothesis in search of a decision tree that correctly classifies the training data. More elaborate. Why we call it as more elaborate hypothesis? Because the tree expands. Initially, it is only with the root node. Then the tree expands. Then the tree expands further to the next levels. Right? That is why we call it as elaborate hypothesis. Progressively, it considers progressively more elaborate hypothesis in search of a decision tree that correctly classifies the training data. Okay. Now, the evaluation function that guides this hill climbing search is what? Information gain measure. When a person is climbing a mountain, the measure is steepness in the climbing. Wherever the steepness is high, if he follows that path, he'll reach the top quickly, or he'll reach the top in an optimal way by not wasting many days or by not wasting his energy, right? Those are his considerations. Now, what are the considerations in building a decision tree in this hill climbing approach? The information gain should be high. Wherever an attribute provides an information gain to be higher, that should be selected as the first attribute in order to perform the classification. Then it proceeds further. There it finds another attribute which provides better classification. It proceeds further until it reaches the leaf nodes or pure classifications at the end of the decision tree. Okay, that is how we treat this information gain as the evaluation function used in decision trees. Now, the hypothesis search space, how it looks like in decision trees. See, initially, a small decision tree is built with the root node and the leaf nodes. Now, at each leaf node, the purity of classification is checked. If the purity is not correct, it proceeds further. If the purity is sufficient, if the purity is not sufficient, then it proceeds further. If the purity is sufficient, then it stops there. Like that, it goes on and on, considering attribute A1, A2, A3, A4, what all the attributes are available. It proceeds with all of them by checking their information gain at each split point and seeing whether the classifications made are pure or not. If it is pure, the tree construction ends there. If it is not pure, it has to further check other attributes. In this process, it is not compulsory that all attributes have to be considered by the decision tree in the construction of decision tree. That is why, did you see in the last class, we have the decision tree has skipped temperature attribute because it is not providing any better classification than other attributes. Right? In that way, the decision tree is constructed. Now, what are the capabilities and limitations of this ID3 algorithm? ID3's hypothesis space of all decision trees is a complete space. Remember, it is a complete space of infinite discrete valued functions relative to the available attributes. Okay, it is in the form of discrete valued functions. Say humidity normal means what will happen. Humidity high means what will be the outcome label. Humidity high and overcast outlook, outlook overcast means what will happen, what will be the end label. Like that, it will be, the data will be considered in the form of key value pairs, and it will check the complete hypothesis space. The hypothesis space is complete. It will cover all the training examples. It will not leave out any training examples. It will cover all the training examples given in the training example set. So ID3's hypothesis space of all decision trees is a complete space of finite discrete valued functions relative to the available attributes. Okay. So if you take humidity, you get a small tree. If it is high, if it is normal. If you take wind, if it is high, if it is moderate, if it is low, what will happen? Like that, you have a finite set of decision trees in this hypothesis space, right? all these subtrees will join together to make the main decision tree. Now, because every finite discrete valued function can be represented by some decision tree, right? You can represent, correct? If you take sky, you have sunny or windy, cloudy. If you take wind, you have high or low. If you take temperature, you have high or low, right? In that way, you can represent every finite discrete valued function with some decision tree. And ID3 avoids one of the major risks of methods that search incomplete hypothesis space. Hypothesis space should not be incomplete, right? It should contain every possible hypothesis that covers the training examples. It should not contain, the training examples should not have any hypothesis that is not contained in the hypothesis space. That is why this ID3 avoids that risk of methods that search the incomplete hypothesis space. Hypothesis spaces are well built with this decision tree learning. Why? Because it has one decision tree for every possible attribute values. Now, ID3 maintains only a single current hypothesis as it searches through the space of decision trees. This is very important. It maintains only a single current hypothesis. Single current hypothesis means only one particular decision tree. It doesn't keep on checking. Say one decision tree is constructed with root node as say Outlook. Now another decision tree is not constructed with root node as humidity. It will construct only one particular decision tree by calculating information gains at each split point, right? That is what is mentioned here. ID3 maintains only a single current hypothesis. What is the hypothesis here? Decision tree only. So ID3 maintains only a single current hypothesis as it searches through the space of decision trees. Lots of decision trees are available, but it will proceed with only one single hypothesis. Okay, unlike candidate elimination method, there it will try to check with every hypothesis. But here, though many decision trees are there in the hypothesis space, it checks with only one particular decision tree, which gives better classification, right? But it loses the capabilities that come from representing all consistent hypotheses. Means it doesn't check other alternative solutions. There are a lot of possibilities available for constructing the decision trees, but once it starts with its ID3 algorithm and constructs the decision tree, other part of the decision, other types of decision trees, it doesn't consider at all. Okay, it goes blindly with whatever decision tree it is constructing by only considering the information gain measure. Okay, so in finders and candidate elimination algorithms, the hypothesis space contains multiple statements which are consistent with the training examples, and the hypothesis space in decision tree contains decision trees that will fit with the training examples. Among those decision trees, ID3 proceeds with only one particular decision tree when it starts calculating the information gain and proceeding to construct the decision tree, right? Now, ID3 in its pure form performs no backtracking in its search, correct, right? It starts with overcast, Outlook. It starts with Outlook. Now, information gained with Outlook is more, so that is taken as the root node. After that, it goes to humidity. Now, will it go back after checking with humidity that whether Outlook information gain is lesser or greater than any of the other attributes? No, it is already calculated in the beginning itself that Outlook's information gain is more. So it has taken a clear decision that Outlook gives the better classification. Then it proceeds to the next level, humidity, temperature, and wind. Right? It doesn't go back or backtrack in order to check whether its decision about Outlook being taken as a root node is correct or not. It will not check again. It will not backtrack again. Right? it converges to locally optimal solutions that are not globally optimal. This is the drawback of decision trees. It will always check its local optimal. That is better information gain. Again proceeds further, checks information gain with other set of remaining set of attributes. There the information gain, whichever attribute is having higher information gain, it selects that attribute. What will happen in this case? It is checking locally at that particular attribute. It is not checking at the level of the entire decision tree. It is checking only locally at that particular attribute. That is why it converges to a local optimal solution, not the global optimal solution. Means after constructing a decision tree, other decision tree also may be optimal, but ID3 algorithm will not backtrack and check its decisions, right? It converges to locally optimal solutions. It doesn't go for checking globally optimal solutions. And ID3 uses all training examples at each step in the search to make statistically based decisions regarding how to refine its current hypothesis. So it will always try to check at particular position whether it can take some statistically based decisions in order to refine its current hypothesis. It uses all the examples. That is why you remember you're counting each and every example where that possible attribute value occurs, and among them how many are positive, how many are negative. You're checking each and every training example in this case. Correct? That is why ID3 uses all the training examples at each step, at each node, at each split point. In order to select the split point, it checks all the training examples. To make statistically based decisions. What are the statistically based decisions? Entropy, information gains. These are all statistical measures which helps to refine its current hypothesis by selecting the best attribute as the split point, which gives the better classification, right? Now, ID3 can be easily extended to handle noisy training data. That is the most important advantage of decision tree algorithms. It can handle noisy data by modifying its termination criterion to accept hypotheses that imperfectly fit the training data. So you can keep on extending in order to fit that noisy data also. Say there is some data which is outlier, which is not fitting with the initial levels, but keep on extending the decision tree. At some point, that noisy data also will be classified, right? By increasing the number of split points. That's it. So you are trying to make your decision tree more complex in case of noisy data. That's all. More than that, there is nothing actually having any less say drawback with this decision tree. You generally try to make the tree more complex in order to make even this noisy training data consistent with the decision tree. That's it. But if you don't have any noise in the training data, you end up with simpler decision trees. You have noisy training data, you end up with complex decision trees. But it covers all the training examples. That is the advantage, right? Now, what is the inductive bias in decision tree? What is the inductive bias in finders and candidate elimination algorithm? In candidate elimination algorithm, the inductive bias is, it doesn't consider disjunction of the attributes. It considers only conjunction of the attributes, right? If we consider even disjunction of the attributes, if this is true, or this, or this, or this, lots of hypotheses will start appearing in the hypothesis space, and it will never end actually. It will go into an infinite hypothesis space, right? So what we learned is, in inductive bias, in order to make a hypothesis generalizable, in order to make say a machine learning model generalizable, you need to have some assumptions. If you consider all possible hypotheses, you cannot generalize the machine learning model. You need to have some assumptions. If you consider all possible hypotheses, you cannot generalize the machine learning model. You need to have some assumptions. If you consider all possible hypotheses, you cannot generalize the machine learning model. If you consider all possible hypotheses, It may not cover the training examples properly, and it may not be able to generalize well to the unseen data. If a new data is given, it may predict it wrongly. Why? Because it covers everything. It covers all possible alternatives. But that should not be the case, because prediction is wrongly happening here. Say where the label have to be predicted as no, it will be predicted as S. Where the label have to be predicted as S, it will predict as no. Why? Because it is okay with any of the values in the attributes. Because disjunction of the attributes is allowed. That will result in infinite hypothesis space. That is not acceptable, because your model will not be generalizable to the new training to the new unseen data given. It can't generalize, it can't predict properly. That is why inductive bias means having some assumption that your model will be consistent only with the conjunction of the attributes. Means this and this also should be true, and this and this. Like that, we are putting a limit on the hypothesis space and avoiding it from becoming infinite. Got it? So this inductive bias is the assumption we make. In finders and candidate elimination algorithms, the assumption or the inductive bias we made is, the inductive bias of the model is, it doesn't contain disjunctive hypothesis. It contains only conjunctive combination of attributes in the hypothesis. That is the assumption. Now, what is the inductive bias in decision tree learning? What assumptions do we make in decision tree learning in order to make the hypothesis set finite? I said, if there is lot of noise in the data, you construct complex decision tree, and you can construct such complex decision tree many in number, not only one decision tree. Lots of decision trees will suit your training examples. Right? Now, in that case, where to stop? Which tree to consider as the most optimal decision tree? In order to arrive at that conclusion, you should have some assumptions. You should have some inductive bias. You should have some bias, partiality in your learning process. What is your partiality in this decision tree learning? Smaller decision trees. What is inductive bias in finders and candidate elimination algorithm? Only conjunctive combination of attributes are allowed. Only such hypotheses are allowed in the hypothesis space. Now, what is the inductive bias in decision tree algorithm or decision tree learning? Only small decision trees are favored. Large or complex decision trees are not opted. Okay, that is the inductive bias. Now, what is the policy by which ID3 generalizes? What is the inductive bias it has? What is the partiality it has in order to learn from the training examples and generalize to the new examples? Given a collection of training examples, there are typically many decision trees. That is what I'm trying to say. Many decision trees consistent with these examples. Now, which of these decision trees does ID3 choose? It should have an inductive bias. Only then it can choose the optimal decision tree, or it has to work with all the decision trees possible in order to make a prediction. Is that possible in the real life scenario? Check every possible alternative with all the decision trees and make a prediction? It is not at all possible. So the hypothesis space have to be minimized. The hypothesis space have to be in a finite, right? It should not be infinite. For that, how does the ID3 algorithm choose the best decision tree from the available decision trees? What is the ID3 strategy? The strategy followed by ID3 algorithm? It selects in favor of shorter trees over longer ones. This is what I have been telling, right? The inductive bias of decision tree learning is it favors shorter trees over longer ones and select trees that place the attributes with highest information gain closest to the root. That is another assumption. It is assuming that information gain, if it is more, that attributes may be a best classifier, right? So that has to be taken as the current split point. That is another assumption. So what is the approximate inductive bias of ID3? Approximate means vague, very brief brief inductive bias of ID3 is shorter trees are preferred over larger trees. This we know. Now let us see the appropriate inductive bias, what it is. Okay, ID3 can be reviewed as an efficient approximation of breadth first search ID3. Why we call it as breadth first search ID3? ID3 algorithm always checks for all the decision trees with one level first. If it is not covering all the training examples, then it goes to the second level and checks the hypothesis space with such kind of decision trees with two levels to cover the training examples. If it is not covering, it goes to the next level, 3 levels of decision trees to cover the training examples. At each stage, it will check the breadth first. First level entirely, it will cover all the training exam, all the decision trees, whether it will cover the training examples. No, it goes to the second level, it goes to the third level. Means first one level decision tree, 2 level decision tree, 3 level decision tree. All these trees will be checked in order to find the best fit decision tree, right? This is why we call ID3 algorithm as breadth first search ID3 algorithm also, which is using a greedy heuristic search. It checks all possible alternatives greedily, right? So using a greedy heuristic search to attempt to find the shortest tree. It always wants the shortest tree. That is why first it checks all the level 1 decision trees. Then only it goes to next level complexity, right? Without conducting the entire breadth first search through the hypothesis space. Okay, so it is trying to, it is attempting to find the shortest tree without conducting the entire breadth first search through the hypothesis space by what it is, how it is limiting. Actually, it can search all the hypothesis space, but it is limiting its search by using the information gain. Okay, hypothesis space contains all possible decision trees. In that you have 1 level decision tree, 2 level decision tree, 3 level decision tree. Now ID3 algorithm performs a breadth first search. First searches all the simple trees, then goes to complex trees, then goes to more complex trees. It keeps on searching, but we are limiting its search by helping it, by providing a measure called as information gain. This information gain will help it to find out what is the best split point in order to make better classification. Wherever a tree is providing such kind of classification, that tree will be selected by the ID3 algorithm. Okay, so we are helping the ID3 algorithm in order to avoid it from searching the infinite search space by helping it with the information gain measure so that it can decide on which would be the optimal decision tree. Now, what is the better approximation to the inductive bias of ID3 now? Shorter trees are preferred over longer trees. That is general approximation, general assumption. What is further assumption? Trees that place high information gain attributes close to the root are preferred over those that do not. That's all. Means you are also making another assumption that information gain is an important measure to find out the split point. Right? So what are the assumptions? Two assumptions we made in decision tree algorithm now. Shorter trees are preferred over longer trees, and while checking them, if information gain is used, it will help the ID3 algorithm to find the optimal decision tree quickly without having to search the entire hypothesis space. Right? This is the inductive bias in decision tree learning. Okay. Now in next class, we'll see what is restriction bias and preference bias. Again, in inductive bias, there are two types, restriction bias and preference bias. So how do we need to select which one to consider? Okay, and why prefer only short hypothesis? Why not go for long hypothesis? Under that, we are going to see the definition given by Occam's razor, the theorem prescribed by Occam's, why we need to prefer only short hypothesis. Okay, these two we'll see in the next class. Now, before ending our class, answer these 4 questions. What is the inductive bias in candidate elimination algorithm? What is the inductive bias of candidate elimination algorithm? I have stressed on this point throughout the class. What is the inductive bias of candidate elimination algorithm? Means what are the assumptions made in candidate elimination algorithm? Students, what is the assumption we made in candidate elimination algorithm? Not we, but that algorithm. What assumption it makes in order to generalize well with the unseen data? Try to answer this, whether wrong or right. You try to answer, then I'll correct you. What is the assumption made by candidate elimination algorithm, or what is the inductive bias of candidate elimination algorithm in order to generalize well or in order to predict well with the unseen data? Disjunctive combination of attributes are not allowed. Only conjunctive combination attributes are allowed. If we say disjunctive combination of attributes are allowed, this is okay, or this is okay, or this is okay. It goes on like that, giving infinite set of hypotheses. That is why, in order to limit that hypothesis space, we are assuming that this algorithm works with only conjunctive combination of attributes. All this combination should be correct. Only then the training example will be consistent. Okay, for this combination of attributes, this training example will fit to this hypothesis. For this combination of attributes, this training example will fit this hypothesis. Like that, you have strict rules, not disjunctive rules, right? This is called as inductive bias of candidate elimination algorithm. It assumes that the algorithm prefers only conjunctive combination of attributes, no disjunctive combination of attributes. So what is the inductive bias of ID3 algorithm? This you can answer easily. Just now we have completed, right? What are the assumptions in ID3 algorithm? 2 assumptions we have made, right? One is general assumption and one is specific assumption. What is the general assumption? Smaller trees are preferred or larger trees?
Shorter trees are preferred.
Very good. Shorter trees are preferred. Smaller, simple trees are preferred. What is the next assumption? What is the next assumption? While selecting among these shorter trees, information gain is used. Statistical measure called as information gain is used so that it can limit its search accordingly. Wherever the information gain is high, that attribute should be selected as the split point in those short trees. Then it can find out the optimal trees which can generalize well to the unseen data. Okay, now what is entropy?
Random information, creation of random information.
Random information, uncertainty in the information, right? Yes, uncertainty means if the classifications are not pure, then we say that the entropy is very high. If the classification is pure, means if the attribute provides a classification of all positive training examples and no negative training examples, in that case the entropy is 0. because there is a certainty in the classification. That is called as entropy. Now, what is information gain? Information gain. Information gain is how better the classification can be made by an attribute. How pure classification can be made by an attribute, right? So as the entropy is high, as the entropy increases, information gain decreases. So entropy is inversely proportional to information gain. If the information gain is high, means if a better classification is made, then entropy is obviously zero, right? If you have only all positive training examples for that branch and no negative examples, in that case we say entropy is zero. But if you have 3 positive examples and 3 negative examples, 50-50. In that case, we say entropy as 1 because there is impurity in the classification. Here there is purity in the classification provided by the attribute, right? That is how entropy and information gain should be used in order to construct the decision trees by considering optimal split points. Okay? Any doubts still here, students? Shall we proceed with the topics or you want me to repeat again the previous calculations? Anyway, video is recorded and it will be provided for you. Take the textbook, work out the training example set given, and also you can search for different training examples on internet, and taking those training examples you can practice how to calculate entropy and information gain in order to construct the decision trees. As this is a compulsory question in your exam, internal as well as final exam, because over this no other question can be given from this chapter, right? So you have to practice this very well and do optimal construction of the decision trees, right? We'll meet in the next class. Bye.
Thank you.